Welcome to another part of the ISM Statistics 1 exercise set, this time with an exercise on measures of contingency. Let's take a closer look at the exercise. A jeweler suspects that man rather buy jewelry which leads to higher profits for him. Over the course of 1 month, he collects the following data set. Use a suitable measure of association, normalized to the interval 0 to 1, to quantify the strength of the association between the customer's gender and whether they lead to high or low profits. First off, which statistic could we use here? Well, we directly see gender as well as the profit variable are more or less nominal in nature. Profit could be ordinal, as we say higher profit is more than little profit, but well, at most gender, that's a typical nominally scaled variable. So here we have at least one nominally scaled variable, so this only leaves like the chi-squared statistic or any statistic built on the chi-squared statistic, meaning contingency coefficients, corrected contingency coefficient or something such. Then we have the information it should be a statistic which is normalized to the interval 0 to 1. So this means we need to take the contingency coefficient and we need to take it in its corrected version. This in mind, we can start. First off, we need our marginal frequencies. How do we get them? We copy our table and add one column and one row. And in these, we add the sum for each column and for each row. As with males, we get a total of 6 males in our sample. We get a total of 70 females. We have a total of 56 sales with little profit. We have 74 sales with high profits, and we have a total of 130 sales. So this in mind, we can already get to go to the next step. And in the next step, we're going to calculate the expected frequencies. For this, we're going to use this formula. However, it's much easier than it might look like, meaning we just copy the table from before. However, we leave blank the cells in the middle, so the cells which originally contained the data we had from the exercise. We only copy our marginal frequencies. And then for each cell, we multiply the corresponding marginal frequency for the column and the row with each other, and we divide this by the overall amount of observations. So for example, little profit and male, we multiply 60 and 56 and divide the result by 130, giving us here a value of 25.85. Same we do, for example, for the other. So for female and little profit, we have 70 times 56 divided by 130, giving us the result of 30.15. Then for male and high profit, we have 60 times 74 divided by 130, giving us the 34.15. And we do the same thing for female and high profit, where we get an expected frequency of 39.85. Then we can finally start calculating our statistic. For this, we can take our expected frequencies and the original frequencies. Here they are summarized in a comprehensive table. So the first values are the original, the actual values, and the values after the slash are the expected frequencies. What we're going to do with them is we are going to apply this formula for the chi-squared statistic. And this basically means we take the expected frequency, subtract the original frequency, square the result, and divide it by the expected frequency. So if we start with male and little profit, we'll calculate 25.85 minus 12, then the result to the power of 2 and divided by 25.85. 5. This is the first part. We do something similar for all 4 parts, yielding the following 4 terms. Here it's interesting to note we have 4 different cells and we will get 4 different terms for the chi-squared statistic. That's a point we will get back later on, and this is also a point which might help one if one's not sure, did I miss something, did I include everything, all the different cells. Here just recall you have 4 cells, so you need to have 4 terms in the chi-squared statistic. Its logic is always the same, it's always expected minus actual to the power of 2 divided by expected. If you compare this, you see for the other 3 cells it's exactly the same thing. Well, if you have written down this part, you can start putting this into your calculator, which in the end will get you a result of 24.2136, being the chi-squared statistic. However, we're not yet finished. We still need to correct our chi-squared statistic for 2 parts. First off, we need to correct it for the number of observations we have, going back to the fact that, well, if we have more observations, there is more potential for the expected numbers and the actual numbers to diverge. And we also need to correct for the size of the contingency table, because for each additional cell in the contingency table, the chi-squared statistic will have 1 additional term which is added to it. So meaning larger tables usually result in larger chi-squared statistics. And well, if we control for both of those aspects, we will get our contingency coefficient k, or the corrected version of the contingency coefficient. How do we go about this? Well, for the contingency coefficient, we first take our chi-squared statistic as calculated in a previous slide. Then we apply the following formula to get to the normal contingency coefficient. We take the chi-squared statistic and divide it by itself plus the number of observations, and the result then we take the square root. So how does this look like for our numbers? So we calculate here 24.2136 divided by itself plus 130, the 130 observations we have. For all of this, we take the square root, and we get as a result 0.3962. Well, this already looks a bit more like what we know, for example, a correlation coefficient or something like this would look like. However, the contingency coefficient itself is still not limited to the interval 0 to 1. For this, we still have to consider the second problem I mentioned above. So we need to still control for the size of the contingency table. This we do when we correct our contingency coefficient. So if we calculate the corrected version, k star. So for this, we first off need some help parameter m, which is basically the minimum of the number of columns and the number of rows. So here we have as a minimum number the 2, meaning with this number we can use the following formula to get our corrected version of the contingency coefficient. So we multiply the original contingency coefficient with this correction term square root of m by m minus 1. Here with an m of 2 we have as a correction factor square root of 2 by 1, so times square root of 2. Meaning, we take our contingency coefficient, here the 0.3962, and multiply this with 1.4142. Get as a result 0.5604, this being our corrected contingency coefficient. And as this corrected contingency coefficient takes values from the interval 0 to 1, we can, well, not totally, but in some parts compare this to what we know about our correlation coefficients. So if here we have a value of 0.56. This is a relatively large value, meaning we have a relatively strong relationship association between the two variables we observed. Well, and this then already concludes this short example. I hope you liked it and you took something away from it. And well, if you want to see more of this type of exercises, feel free to visit the rest of the ISM Statistics 1 exercise collection. Until then, see you and goodbye.